Hi, hello. Actually, the three previous papers are about membership inference. Our paper will be on a different path. We will talk about model extraction attack. Okay, let me see. It works. Okay, so nowadays we have many cloud giants provide machine learning as a service, which allows users to access the large models on the cloud through an API. So that gives rise to, or gives motivation to model extraction attacks, where the attacker aims to learn the private information or to establish a substitute model with similar functionalities to the target model. The benefits can be multifold. So on the one side, the attacker may establish their own machine learning as a service and undermine the pay-for-prediction pricing model of the previous service provider. Or it has been proved that model extraction attacks can facilitate the adversary to carry out further privacy attacks, for example, membership inference attack, and the evasion attacks by turning the black box model into white box models. Usually, we conduct the model extraction attacks in 3 steps. Firstly, the attacker will initialize a substitute model, for example, with random parameters or with a pre-trained model. Then, the attacker will query the target model and obtain the query results. Finally, those query results will be used to retrain the substitute model. So it's kind of like learning from the expert of the black box target model. Of course, in this cat and mouse game, because we have attacks, people certainly come up with the defenses, and mostly they use disruption-based defenses. The key idea is that because the attacker retrains the substitute model with a query result so that the defender can disrupt the query result to mislead the attackers. For example, in this case, after the victim model has yielded the output, random noises will be added to the output and then returned to the attacker. This disruption-based defense motivates our work to come up with a defense penetrating attack, which we named it as D-DAE. It can be integrated with existing extraction attacks because we have come up with a plug-in framework which consists of a disruption detection and a disruption recovery module. The disruption detection tries to infer what kind of defense has been adopted by the defender by looking at the distinctive distribution of the queries. And the disruption recovery will use a generative model to try to restore clean query from the disrupted ones so that the clean ones can be used to retrain the substitute model. Finally, we have conducted evaluations on multiple defenses and real-world APIs. Before I dig into details, I will clarify our threat model. We assume that the attacker has access to public data sets, can query the target model, and can reconstruct the defense strategies. And however, the adversary cannot access the target model, the original training data, or the knowledge of the specific defense strategy. And to actually realize our goals, we have to solve 2 challenges. The first is how to detect the specific defense mechanism adopted by the defender, because usually the defender will randomly alternate between different defenses to avoid being detected. So the difficulty is that we may not know the specific defense. So our solution is to train shadow models with different defense methods, and we then use the outputs of the shadow models to train classifiers to try to detect the different defense methods. And the second one is how to recover the disrupted query results because random noises are added to different queries. So we train generative models also by the outputs from the shadow model. And so let's look at the first module of the disruption detection. So our idea is to train a pool of, first to train a pool of unprotected shadow models with different structures and possibly with different public data sets, because we do not know the specific structure of the target model. And then, because we assume that the attacker can reconstruct the defenses, so the attacker applies k different defense methods to multiple shadow models. And then we can train binary meta classifiers. Actually, we train one meta classifier to each defense methods, so using the outputs from the shadow models. Then, after the specific defense method has been detected, we recover the clean query results by using a generator. Here is the specific design of our generator. We actually use the batch norm layers, the leaky ReLU layers, the fully connected layers to transform the disrupted output into a clean one with the data from our shadow models. We evaluate D-DAE using two metrics commonly used in model extraction attacks. First, we concern about the model accuracy of the substitute model, and sometimes if we try to do black box attacks, we may concern more about the agreement, whether the output of the substitute model is the same as the target model. So we evaluate those two metrics. And we kind of integrate D-DAE with three existing model extraction attacks, the JBDA, knockoff net, and active thief. And we used five training data sets with different model structures. We evaluate 7 defenses. Those are all disruption-based defenses, including adding different noises to the output or using ensembles of diverse models to try to to try to disable the model extraction effort. We also consider hybrid and unknown defenses. In hybrid defenses, actually, we assume that the defender alternates between two different defense strategies, or they kind of perform rounding after EDM, perform one defense after a certain defense. And we also perform unknown defenses, where we train the shadow model, the meta classifier, and the generator using some of the defenses, but evaluate the performance of D-DAE on a totally different defense strategy. Okay, we show that actually our model extraction attack can reach higher accuracy and higher agreement than existing works, kind of improve the existing model extraction attacks under different defenses and the hybrid and the unknown defenses. This is the result from the ImageNet data set, and more results will be in our paper. Okay, we evaluate the effectiveness of our disruption detection module, and we can see that our meta classifiers can reach very high prediction accuracy of the disruption detection. And we also show that our disruption recovery module actually has transferability if we train the generator on some data sets, but try to extract the model that is trained on other data sets, we can have good performance. Also, our shadow models is effective under different model structures. Then we apply our model extraction attack to real-life APIs we conducted for Microsoft Asia and Face++ with absolutely unknown defenses. So we can also show that with our plugin framework D-DAE, we can improve the existing model extraction attacks. Of course, we have several limitations. First, we target at disruption-based defenses and not detection-based defenses because there are also detection-based defenses that tries to detect whether certain kinds of queries are trying to extract the models. So we did not evaluate whether our attack can evade those kind of defenses. And we have not evaluated our attack under DP-based disruption because we have, upon the time of our publication, there are as far as we know, there are 2 papers about DP-disrupted model extraction defense, but the authors haven't published their codes yet. And then because we have to train a lot of shadow models, the cost of our method may be high sometimes. In conclusion, we propose a defense-penetrating model extraction framework. The key idea is to first detect what kind of defense has been adopted by the defender, and then we try to recover the undisrupted ones by a generator. And our extensive evaluation has, there are some typos here because I'm not able to update my slides today. We have evaluated actually 7 defenses and 3 baselines. Thank you very much, and I'm glad to take questions from the audience.
Yeah, thanks for the talk. So I had a question. I was a little confused with the threat model. So you said that the transferability is high in the stolen models to the original model to launch adversarial attacks. But doesn't that make them also detectable to the, like that they're linked with the stolen model? Well, yeah.
Oh, actually we did not consider whether the extracted model will be detected as a replica of the original model. We just consider it's a success if we can establish a substitute model with similar functionality, but does not consider whether it will be detected later. Maybe we can use it stealthily,
okay.
the extracted model.
Hi, thanks for the inspiring talk. For the 7 defenses considered in your paper, will they use any hyperparameters which can affect the performance of your defense? And if so, suppose an attacker knows the defense but doesn't know the hyperparameters, will it affect the shadow training process?
Oh, good question. Actually, the 7 defenses, some of them in my slides, actually, they have hyperparameters. For example, the magnitude of the maximum noise is added to the queries, and we show that it indeed affect the effectiveness of our extraction. But again, for the defender, the choice of hyperparameter is a trade-off, because the higher the magnitude of the noise, the more privacy will be protected, but the utility of the model will be affected. So I think it's a trade-off for the defender and also something for our attacker to consider about.
Hi, I have a quick question. Nice talk. As you say that your work, D-DAE has a very good transferability among different defenses, right? So which implies there are common information in the model's output, no matter what the noise added on this output, right? So what's your insight that can support your strong transferability between different defenses, even those unknown defenses? So what makes your work successful on those unknown defenses?
Okay, thank you. Thank you. A very good question. Actually, I wouldn't declare a strong transferability. I would say some transferability. I think that there is similarities between the 7 defenses that we evaluate, and I think that the transferability is due to such similarity. And if there are further more different defenses, I'm not sure. That may be an open question to explore in the future, whether our attack can still transfer to those defenses. Thank you.
Thanks, Yanjiao, again for her great presentation.